Okay, so now we're going to start on chapter 7, which is similarity. Okay, and so the question is, say we're an aircraft engineer and we're designing a big giant airplane, something like this. And here's the wings. A pretty bad airplane. Now we want to measure the lift of the wings and the drag on the airplane hull and things like that. And so as the air goes over the airplane, you'll have some sort of drag force, some sort of lift force that is trying to lift it up, and things like that. And so as you're designing it, you actually want to know what these are. However, you can use CFD to do these to a certain extent, but at some point, you're going to have to do experiments and go to the wind tunnel. But the problem is that this is way too big to fit in a wind tunnel. Okay, and so because of that, it is not practical to do an actual drag force measurement on an actual large-scale aircraft. In most cases, maybe some small aircraft you could, but say you have a big B-52 bomber, there's no way that you could fit that in any real wind tunnel. So then, you could intuitively think, well, what we're going to do then to make it fit inside of the wind tunnel, if this is the wind tunnel, is we'll just take the plane and we'll shrink it down to something that can fit inside of the wind tunnel. So that's a scale model. Okay, and then in this wind tunnel there will be some sort of airflow going over it, and you'd measure a drag force and a lift force acting on the scale model of the plane. But now the question that we need to ask is, first, how do we select V, the airflow velocity V in the wind tunnel? Right, so that's a big question there. Is that if the aircraft here is flying at 500 miles an hour, do we choose V in the smaller wind tunnel to be 500 miles an hour? At least to me, that is not an obvious question to answer. Then is how does the measured quantity scale in the wind tunnel to the real world? So that is we're going to stick a smaller scale model of this plane inside of a wind tunnel, and we're going to be measuring a drag force. So not only do we need to pick a velocity V so that it's relevant to the real world, but then we also need to think of, we're going to measure a drag force that's clearly going to be the magnitude of this drag force, because the plane is smaller, is going to be smaller. So then if we want to apply our measurements on the smaller aircraft in the wind tunnel, how do we map those measurements and apply them to our big aircraft where we are actually designing? And so that is what we mean by similarity. And so we want similarity between the real object and the test or scale model of the object. Okay, and this requires several things: that the streamlines are similar, and first of all, there's geometric similarity. So what I mean by geometric similarity is that the object that we put inside of the wind tunnel is just a shrunken down version of the real world object. So, for example, you could not expect the drag force to be similar if we want to measure it on, I don't know, this triangle like this, and we have the flow going over that, and we want to measure the drag. Well, in the wind tunnel, if all we have are squares, we cannot do that. That would not work because we do not have geometric similarity. Is that there is no reason to expect the drag force on a triangle to be comparable to scale in any way to that of a square. Okay? And furthermore, we need the streamlines to be similar. So if we want to measure the drag force over a circle, and the streamlines will look something like this, that is, we need to pick a flow condition such that the streamlines look similar. And so this would be a scale of the real world object where we are measuring the drag. And in the wind tunnel, what we need is to choose the velocity v such that the streamlines going around the object are also geometrically similar. So real object and smaller object. Okay, and this is V in the wind tunnel. And we'll show in a little bit that this V of the real world object and V of the wind tunnel are actually going to be two different V's, because due to the size differences, if I chose the same V, oops, sorry about that, I bumped the screen, I keep doing that. If I choose the same V for here, I'm going to get completely different. I'm going to get a completely different streamline patterns. For example, I could get streamlines that look something like this. Okay. And so I need to choose V very carefully, such that the streamlines are a shrunken down version of the streamlines going over the real world object. And if I choose V improperly, I could get a completely different flow pattern over the object in the wind tunnel. Okay? And so how do we go about doing this? Is first we achieve a similarity. Okay, so first you need to think of all relevant flow variables that affect your quantity of interest. Okay, and so say for example we want to measure the drag over a sphere. Okay, and so we'd have some diameter d for the sphere, and we'd have some fluid going over and around the sphere, and that fluid will be coming in at velocity. I'll call it v infinity, which just means the velocity very far. V infinity means the velocity very far upstream of the sphere. It'll be coming in at some density. I'll call that rho infinity. It'll have some viscosity. You could think that the viscosity is going to cause shear stress acting on the surface of the sphere, and so that's going to influence the drag over the sphere. It's clearly going to depend on the diameter of the sphere. I think it's fairly intuitive that if I have the same velocity and a larger sphere, then the drag force on that larger sphere is going to be larger. Okay, and then I'm going to do one last parameter, and it's also, in general, it also depends on the speed of sound. Okay, because in general, the drag over a sphere that has a flow that is less than the speed of sound going over it will be completely different than the drag over a sphere that has supersonic flow going over it. And so you should expect it to depend in some way on the speed of sound. So then we have picked our variables, and in other circumstances, the drag force could depend on some other variables. It just depends on what your specific situation is. And so thus, we expect drag to be a function like this, that the drag force d equals some function, which we don't know, of the free stream velocity v infinity, the density of the fluid. You could expect, you would intuitively expect the drag force on a sphere in flowing water to be much higher than that of air, because the density of the water is about 1,000 times higher. It would depend on the viscosity of the fluid, the speed of sound, and the diameter of the sphere. Okay, so we expect the drag force to be a function of these 5 things. Now, there's a problem here that I want, if you're designing the object, and you expect this sphere to encounter a wide variety of fluids and flow velocities, that means you would need to map out the drag force as a function of all 5 of these variables. Okay? So in this case, the drag force is a function of 5 variables. Okay, and this means that you would have lots and lots of experiments, which I suppose is which is bad in most cases, unless you're a consulting firm doing the experiments, and then you get lots of money doing a lot of needless experiments. Okay, so how do we reduce these tests? Because you could think of, if you have a matrix of basically test runs where you're where you're going to measure the drag force, your test matrix it'd be a 5-dimensional matrix. So if I want to measure the drag force at 5 different velocities, 5 different densities, 5 different viscosities, 5 different speeds of sound and five different diameters, this would require 5 to the 5th experiments. Sorry, I keep bumping that up arrow. This would require 5 to the 5th experiments, which is clearly a gigantic number and not practical for most cases. So how do we achieve similarity and reduce? So how do we reduce the number of test variables? Okay, so not only do we need to find a way to scale v infinity, rho infinity, mu, speed of sound, and diameter so that we can measure a relevant drag force in a wind tunnel, but also we would like to reduce this. We would like to reduce the number of variables that we actually need to test so that we can practically do them in the experiment or use computational fluid dynamics or something like that. Well, there are really multiple ways of doing this. In the book, in the first one, I'm not going to do here. It's a bit it's more of a grad level thing, and so there are multiple ways of doing this. And one, which is the most rigorous, is to non-dimensionalize the governing equation for your system. Okay, so if you're solving Navier-Stokes, you have to non-dimensionalize the Navier-Stokes equations. If you're doing some sort of simplified model and you're deriving your own differential equations, you need to non-dimensionalize those differential equations if you want to use this approach. And you non-dimensionalize this based on, you choose a relevant length, time, velocity, etc. scales. Okay? And you then non-dimensionalize the equations basically based on these. So for example, if you non-dimensionalize the Navier-Stokes equations, you get that partial v, partial t star, and I'll define what I mean by star in a second, v star dot grad v star equals minus grad p star plus 1 over re, I'll define re, times the Laplacian of v star. Okay, and v star is the dimensionless velocity, and that is simply v divided by v infinity over our sphere. P is non-dimensionalized, so p star is a dimensionless pressure, and that's defined, I'm going to define that as v over rho of v infinity squared. There are lots of ways of doing doing this one here. Oops, that's a bad infinity. I will fix that. Okay, and oftentimes for this scaling, you will often see a 1/2 here. Okay, and then we have this goofy parameter here, re. When we go with when we move on to chapter 8 and 9, you'll be dealing with re a lot. And re is called the Reynolds number, and that's rho infinity, v infinity, d over mu infinity. Okay, and so this is the most rigorous way of doing this. And when you non-dimensionalize it, you get these dimensionless parameters here. And in fluid mechanics, RE, or the Reynolds number, that is one of the most important non-dimensional numbers in all of fluid mechanics. And the most rigorous way of deriving that or coming up with it is to non-dimensionalize the Navier-Stokes equations. And again, I'm not going to show you how to do it in this class, but you can see CH7 for more details on that if you're interested. Okay. And the other way of doing this is to use the Buckingham Pi Theorem. Okay, and to use the Buckingham Pi theorem. Okay, and I will stop this lecture here to try to keep the video somewhat short. And in the next video, I will discuss the Buckingham Pi theorem, and I'll show you how to use it by means of example.